Hi everyone, nice to meet you and thank you for the introduction. And today we are going to talk a bit about distributed graph analytics and how can we speed up the distributed graph analytics, because it's not a simple task. Graphs tend to explode, vastly explode when you analyze them. And I'll tell you a few tricks we are using at Одноклассники in order to speed it up. But we're going to start with a small description and few numbers about Одноклассники. So what actually OC is. First of all, OC or Одноклассники is a very large international project with a very large audience. According to the Mediascope research, recent research, almost half of Russian population use Одноклассники. So roughly every second person in the room is an Одноклассники user. Yeah, I know it doesn't work that way, but still it's tens of millions of daily active users and close to hundreds of millions of overall active audience. It's a very large project. It's one of the top 100 internet portals of the worldwide. So why are all those people visiting us? First of all, they're visiting us, they're using us in order to communicate with their relatives, with their close friends, with people that they like more. More than 800 millions family connections are in our social graph. So Одноклассник is really very concentrated about family and close interactions. And of course, people do not only communicate, they produce and consume content. And content at Одноклассники is a bit different from the other social network. For example, if you compare with Facebook, you can see that most content in Одноклассники are in Russian. So sorry for those who don't know Russian. And the important thing that content in Одноклассники, it's more personal, it's more positive, it's more about sharing the true, sincere feelings, not about just arguing about politics or whatever. So it makes a really difference between Одноклассники and many other social networks. And of course, Одноклассники is a very heavy technological project. So we have more than 10,000 servers around the globe, and they're serving up to 2 terabits per second of outgoing traffic, huge software code base, almost 400 and more software components, so high load, fault tolerance, it's all about us. And of course, the big data. We have one of the biggest Hadoop deployments in Russia, and I think it's also one of the oldest one. We started with Hadoop in the year 2012. And as of now, we have 3 clusters, not counting the different sandboxes. And the largest cluster have more than 60 petabytes of data, 10,000 cores, almost 100 terabytes of RAM. And this hardware is not just resting, it's working hard. We have more than 400 daily jobs, streaming jobs, and even more ad hoc queries and different jobs started for explorative analysis by data scientists. And today we are going to talk about special kinds of jobs we are running on our Hadoop clusters, intended to mine some useful information from a social graph. And actually, social graph is a very important piece of information. And you can answer many different questions by looking at the person social graph. For example, we can ask a question if we have a piece of a social graph for a certain user. We can ask a question, for example, how old is he? This might seem silly for a social network where users used to fill their age and other demography data in the profile, but actually in many cases users tend to temper their age for different reasons. Some people want to look younger, some people want to hide from certain kind of advertisement campaigns or just joking. But on the other side, from point of view of different recommendation systems, and we have a lot of such of systems in OC, it's very important to understand the properties of the user, including his or her age. And actually, the social graph can help us, for example, to recover the user age. We just need to take a look at the age of his or her friends, because people tend to be friends with similar users. It's a principle of homogeneity. And looking at the Bob social graph, they see that he has 3 teenager friends, and we can think that probably Bob is actually a teenager. But he also have 3 more adult friends, and we cannot be quite sure. So we need some additional information in order to make a more confident, more precise decision. And in order to get this information, we can take one step further and take a look at the so-called ego subgraph. Ego subgraph is a part of the entire social graph which is visible by a certain person. It means that ego subgraph includes the person direct friends and links between the person friends. And in case of Bob, we can see that Bob is not only having 3 teenager friends, but he's actually part of the dense community of teenagers. And having this additional information, we can make a more certain decision that Bob is actually a teenager. And this kind of graph, Hegel subgraphs, actually can help us to answer many different questions. Apart from the user age, we can reason about users' tastes in different areas in music, videos, books, and etc. We can even ask a question if our user is a human being, or is it a software which is trying to emulate a user for different malicious purposes. And we can answer a question whom else Bob might be interested in to become a friend, and many more. So it's really a very important piece of information. And before going further, we need to make some clarification. So ego subgraph is only a part visible by the user. So if one of the Bob's friend, in this example Gary, has an additional friend, let's call it her Ilona, which is not in friend with Bob. So Ilona is not a part of the Bob's ego subgraph. So ego subgraph includes only the direct friends and links between them. And that's important, and we will use this property for optimization later on. So let's keep moving. This is a very useful piece of data, but it's pretty hard to get it because graphs, they tend to explode, vastly explode, and you try to analyze them. For example, if you have an average user with 100.5 friends, when constructing a subgraph for him or her, we can get subgraph with up to 11,000 of links. So this ego subgraph will be 100 times larger than the original graph. It's even worse if you take an active user who can have up to 5,000 friends, and for 5,000 friends we can get an ego subgraph up to 20 millions of links in the ego subgraph. So it's more than 2,000 larger than the original graph. And it causes some problems, but not only these. If we are working with a large graph, of course, typically large graphs are not stored on a single machine, they are distributed and partitioned. And the default strategy, which is most commonly used, they are partitioned just by user ID. So we also use this strategy. And in this case, in order to get information for a user ego subgraph, we need to get information from all his friends. And in order to do so, we need to access data from many partitions. And actually, in most cases, it means that we need to access data from all partitions. It goes kind of all-to-all shuffle, creates an enormous network traffic, and actually the running time of constructing these graphs from the distributed graph can be very large, and we will see it later on. Sometimes we try to mitigate this by constructing parts of a subgraph in runtime, but it's also pretty hard because if we have to ask many partitions in a distributed system for a data, there is a very high high chance to get a high latency response, and for extreme users we have an acceptable extreme time. So it's not a solution. We need a way to construct the Ega subgraphs in the analytical phases on a Hadoop. Let's try. We will take a look at a bit simplified example. We have a graph. Initially, it's represented just as a table where each row is a user, as a key, and a set of his or her friends. And we want to construct the Ega subgraph. What we need to do, so first, the straightforward way is we convert the initial representation into two sets of pairs. First sets of pairs, it's user and his friend, and all the pairs. And the second set is a friend and a user he's friend with. So we just have two symmetric sets, and in order to get the Ega subgraph, we need to join these two sets of pairs in order to get a set of triples. Here, each triple actually represents a path in a graph of length 2. And by grouping all these triples into a single structure, we can get the final Ega subgraph. And after we do the grouping, we need not to forget to filter out the external links. And this actually also an interesting point. So you already might note that we are actually passing a lot of relevant data across the network, which we will need to filter later on. But the straightforward approach works just like that without any additional tricks. Let's take a look how it will look like in code. So usually with Alexei we work in pair. Alexei Zinoviev, say hi. Usually Alexei makes some introduction to Spark in his talk, but not today. So today I'll have to tell you a bit about Apache Spark before going further. So all the code we will see today is a fragment from the Apache Spark. Apache Spark is a distributed platform for making distributed computations in a kind of MapReduce fashion. It has different APIs for working with data. A high-level API, which looks very similar to an SQL, but in code, and a low-level API, which is just like a MapReduce. So here it's an example of a Spark code written in Scala. So we just need to read a graph which is stored in a Hadoop file system, and the graph will look like a table or data frame in terms of Spark, where each row has a user ID as a key and an array of friends. And each friend or friendship is described by an ID of the friend and the type of link. And for today we will need only IDs. We won't look at the links type. What we do next, first we need to convert the graph from original representation into pairs, and we simply do a select order the graph and using a built-in function to explode. So if we have an array of IDs, we can explode an internal column of type array into a set of rows. And this expression actually gives us a set of pairs we need to work with. And then literally we're following the schema. We just join the set of links on itself, group the resulting data set by ID of the user, and construct the final representation. So it looks very simple. Basically nothing can go wrong. We just start the job, waiting for the result, and after a few hours our data center looks like this. And unfortunately this is not a joke, so it's a real case. Then I was preparing the code examples for the conference. We got a fire in one of our data centers. Fortunately we do not have any downtime, so we are really fault tolerant. We managed to survive even a burning data center. But the job for calculating Ega subgraph, it didn't succeed, and it actually had no chances to succeed. with our default setup we are using Apache Spark with, it will eventually fail. It will run out of memory and create enormous traffic and fail. Our default setup for Apache Spark looks something like that. So we use up to 511 executors. With dynamic scaling, Apache Spark can shrink and extend the amount of executors it consumes. And each executor has 16 gigabytes and 4 cores. So with default setup, the job we have written it as in a straightforward way, it has no chances to complete, it will fail. If we optimize the setting, so basically consuming all the cluster for 20 hours, we can succeed. So we can achieve that the job is completed. But running a job for 20 hours, consuming the entire cluster is not an option, because we want to do much more in the cluster, and we are not ready to have a job which is running for 20 hours and not letting us to do anything else. So it's actually a no-go solution. We need to do something else. In order to do it better, we can rely on some properties of a social graph. In Одноклассники, social graph is symmetric. So if Alice has a friend Bob, then Bob has a friend Alice. And using this property, we can optimize the process. First of all, it means that we can reconstruct the parts of a subgraph for a user, looking not at his social graph, but at social graph of his friends. And second, we can actually emit twice less information but assuming that we only emit information about the link between two users if the user on the left side of NH is high in an alphabetical order or in any other order than the user at the right side on the NH. So if we know that age is asymmetric, the information will be enough. How it looks like. So how you can see from the picture, we can actually reconstruct the Ege subgraph for a Bob, even do not looking at the graph for a Bob himself. So what we need actually is the graphs from all his friends. And looking at the graph of a friend, we can actually already emit all the triples for a Bob, which are passing through this particular friend. And here, just in one go, we already can create all these triples, and then we can group them by constructing the entire subgraph. And if you also apply additional filtering, for example, if we do not emit an H from Alice to Charlie, only from Charlie to Alice, it doesn't cause any information loss. So in the resulting Ege subgraph, we will still have an H between Alice and Charlie because we've sent it at least once. And if you take a look at Ilona, in this case, if Ilona is not a friend of the Bob and we filter out her from the initial shuffle, we won't see her in the resulting Ege subgraph. It's a good thing, but it's still not enough, because here the filtering is very simple. We rely on alphabetical order, and still we will have a lot of those external links we will need to filter out in the later phase. So how it look like in the code? We need to define basically two functions. First function takes information about user and his friends, and emit information about all the triples passing through this user. And we can represent this information as a record with k of two longs, ID of one user and ID of friend, and emit already a set of accessible users. In order to do so, we take the original friends, we apply the filtering, because as we remember, we filter out them in alphabetical order, or if we are working with IDs, just in a numerical order. We can sort it, and sorting is actually important because later on it will help us to speed up the merging phase. And then for each friend, we just emit all the triples we can get using this friend and current user as an intermediate user. So how it works, just like it took take a look at a simple example. We have a user, let's call 20, and he has 4 friends. When we apply a cross graph function, we will have 4 triples outside. All these triples are actually passing through the our current intermediate user, but they are made from all of his friends. And all these triples are actually parts of the user's ego subgraph. We just need to merge later on. And they are pointing to the all users accessible through the current user. The important question then is how to store the graph. Actually, if we take a look at the graph as it originally stored, especially if we try to make this layout in memory, we usually think about some hash tables, or whatever, or dictionary with dictionaries. Actually, it's a very inefficient way to store graphs if you are using primitive IDs for the vertices and primitive data elements on the vertices and edges, because as you know, when you put the data into a hash table, you have a lot of overhead for boxing, for linking, you have a lot of cache misses, and etc. So what we actually want to achieve, a compact and fast representation of the graph, and we can do so by employing some ideas from sparse matrices representation. And it looks very simple. We can represent a graph using only 3 arrays. First array includes the users, so it's source vertices of our graph. Second array includes indices. Indices, it's actually pointers to the third array, and they points to the place where the friends for the certain users start. So here we just encode a social graph of 3 users using 3 arrays, and we see that Alice is our first user. Her friend starts at position 0, and friends are Bob and Charlie. And same is for Bob. His friends start at position 2, and they are Alice, Charlie, and Gary. And this is a very compact representation. It has almost no overhead for boxing and use memory efficiently. But we need to write some code in order to merge all these triples we emitted from a previous phase into the final structure. And here is the merging routine. So we won't go deeper into that, but you can download slides and take a closer look. What we'll take a look at is the signature of the method. It as an input, it has a fragments of the graph. So we have a friend and a set of friends of a friend. And we have all this information for all our friends. And what we need to produce is basically three arrays. My friends, indices where the information about friends of the friends start, and an array with IDs of the friends of the friends. And to see how it works, let's again consider a simple example with numbers. We have information about 5 friends and the friends of the friends. We have all these 5 friends in the area of friends. We have information about where the friends of the friends starts in the third area and the area of friends of the friends. And which is important, during merging we can filter out. So in the third array we put only friends for those we know the direct friends. So for example, you see the users number 4 and number 7, they are not listed in the friends of a friends list because they are not a part of the nega subgraph. They're external according to the user we are currently looking at. So having these two functions, crossing and merging in place, we can define a code which combines all the things together. Again, we are working with Apache Spark, so we have a graph data frame, and we start with selecting information about user and friends. Here we do not do any explode, we just use an array of IDs. But in order to go further, we need to switch to a low-level API of Apache Spark. So previously we used a very SQL-like API called data frames. Now we are switching back to the original Spark API based on RDDs, or resilient distributed data. And here we actually talk with Spark in terms of map reduces, basically. So what we do, we apply map operation, and here the map is our cross-graph routine. Then we are doing a shuffle. We're repartitioning all the data and sorting by a K. And here K is a pair of users, but we want to partition in such a way that information for the user, a single user, gets to the same machine. So we're using on the first part of our K as partitioning. And after we've done a shuffle, we can group the resulting data set and apply our merging routine. And at the end, we just convert the low-level API back to the high-level data frame. And what we get is just a data frame with rows with a user ID as an ID, and 3 arrays, as we described: array of friends, of indices, and friends of the friends. When we start that, in less than an hour, actually the first phase completes. So the first phase means the emission of the set of triples we need to merge. And it's already a success because previously we failed way before getting all the triples. But it's not good enough, because after a while we still fails, so we run out of memory trying to merge all the graphs. So here we still not working. Our data centers now fine, they are not burning, but task still fails with out of memory. If we optimize it by giving more memory, less cores, we can achieve, we can get it working, and it will work in about 6 or so hours. It's already feasible, but still too hard. So 6 hours for exclusive cluster consumption, it's pretty a lot. So we need to do even better. What can we improve? So the main question here actually is how to avoid shuffling these external edges. If looking at the Gary's social subgraph, we knew that Ilona is not a friend of Bob, we could skip shuffling it. So we can do not include a triplet for Ilona, and it will actually reduce shuffle 10 times, because most of the edges we are shuffling here are actually external edges, not internal ones. But in order to answer the question whenever Ilona is a friend with Bob by looking at Gary, we need somehow to get the entire social graph into memory, or at least to learn how to answer the question whenever 2 users are friends or not, without shuffling the data. And fortunately, we have a data structure which can help us to do so, and the structure is called Bloom filter. I'm sure most of you are familiar with Bloom filters because they're used a lot in modern databases, but in a few words, it's a structure which, based on hash functions, we compute several hashes from our input. In our case, input is a pair of users which are linked in a social graph. It's stored in a bit set, and we can check whenever an element is present in a Bloom filter or not by again computing the hashes and checking if the bits are set or no. If Bloom filter says that users are not connected, then they're for sure not connected. If a Bloom filter says that users are probably connected, then they are probably connected, but maybe it's a mistake, it's a false positive mistake. Still, the rate of false positive mistakes in a Bloom filter can be controlled, and it's a trade-off between size and precision, and with a reasonable precision we can pack with the entire social graph into 5 or 6 gigabytes. One filter of a size 5-6 gigabytes, and it's actually very feasible. So we can easily fit 6 gigabytes into memory of 16 gigabytes executor. And let's try. So how it looks like. First, we construct a Bloom filter from a graph. We need to do it once, and later on we can actually reuse this Bloom filter in many operations. And by having this Bloom filter in place on the second stage, when we are emitting the triplets, looking at the Gary's subgraph, we know that Ilona and Bob are not related, and we do not emit the Ilona's age. So basically what we have in a shuffle in this particular example is absolutely required minimum needed to reconstruct the Bob EGA subgraph without any additional garbage in a shuffle. How it looks in code? Actually very simple. We need only very few modifications. First of all, we need to load the Bloom filter itself. If you knew Apache Spark, you might heard that it has its built-in tooling for loading data on the all servers. It calls broadcasts, but the broadcast doesn't work well with large data, so you can broadcast hundreds of megabytes, but if you start broadcasting gigabytes, you might run into troubles. You need to allocate more memory. That's why we are not using broadcasts to distribute the Bloom filter. Instead of that, we're just using a singleton object, which is initialized on each executor and load the data for Bloom filter from Hadoop distributed file system. We need to modify our cross-graph routine, and just by applying the filtering. So we're emitting a triple only if Bloom filter says that these two persons might be connected. And finally it works, so it takes a bit less than an hour, and we get all the EGA subgraphs. And this is actually already feasible. It's not just feasible, it's kind of normal. So we have a job in the default setup, which means that it does not consume the cluster exclusively. It uses part of it and it scales dynamically, and it takes only 1 hour. So it's just a normal routine job, and we can afford it and base additional jobs on its results. But we can do even better. Actually, we can solve the problem without shuffling at all. It might sound strange, because if we have a distributed graph, how can we construct the EGA subgraphs without shuffling? But actually, if we have a Bloom filter, which is a representation of the graph stored in memory at each executor, we do not need to shuffle. Just by looking at Bob's EGA subgraph and having Bloom filter in memory, we can answer a question whenever Bob friends are interconnected with each other, and reconstruct the EGA subgraph. Of course, this EGA subgraph won't be precise. It will contain some extra edges depending on the Bloom filter precision. But it works pretty fast. So with a map-only phase, we can get the EGA subgraphs in 10-15 minutes. So comparing to 20 hours we are starting when experimenting and burning data centers. But it works only in certain cases. If we need to mine some features from EGA subgraph, like scalar features, for example, we just want to count the triangles, how many friends of the Bob are interconnected with each other. It worked well, because if we know the probability of getting the unexisting age from a Bloom filter, we just can correct the final answer without triangle counting and get a number very close to the reality. And this will be a very useful feature for machine learning. For example, triangle counting is a killer feature for bot classifications. So because malicious software so far are not that good at creating a natural social subgraphs. But in certain cases it will fail dramatically. For example, if we want to analyze the community structure in a Bob Ega subgraph, and for example, we'll try to find connected components. It's very useful tooling. Connected components can help us to improve, for example, friend recommendations, but if we use a Bloom filter to reconstruct it without shuffling, then we will get an extra H, and looking at the two sets of users and checking whenever we have links in between them all to all, there is a very high probability that at least once we will have a false positive result, and it means that it will just merge two connected components together. But if we use not just simple connected components algorithm, but we use more sophisticated clustering or community detection algorithm, it's kind of questionable. Some community detection algorithms can tolerate the noise introduced by Bloom filter, some are not. So there are still cases when we do need to construct the exact Ega subgraphs, and in this case we have to do shuffling. But Bloom filter will still help us to remove the noise from the shuffle itself. But let's take a look on how to construct the Bloom filter from a graph, because there are also some tricky things there. So how it works currently? Basically, we have a graph which is stored in a distributed file system in Hadoop, and first we apply a hashing. So we take each pair of the users and compute a hash from pair of IDs. Of course, we also use the symmetric property, so we always ensure that ages and so the link in the pair are also ordered in the same way, so in alphabetical or numerical order. And having all these hashes, we can just merge them into a Bloom filter and write it into Hadoop distributed file system. I think it's already obvious there the problems are in this schema. It's mainly bottlenecks. So merger, which is a process which combines all the hashes into a single Bloom filter, obviously becomes a bottleneck, which is not that obvious, not the merger itself, but the fact that the Bloom filter stored as a single file also becomes a bottleneck. Files in Hadoop file system, they are divided into blocks of a certain size. By default, it's 128 megabytes, and each block is independently replicated. But in our case, a file is created by a single worker, and the default policy for Hadoop file system, when you create a file, you create a block, and the first replica for a block always located at the node which created the file. So the first replica for each block will be located on a single machine for the entire filter file. And when we are starting to read this file, the default policy again for Hadoop is to just pick replica randomly for each block. And for 5 gigabytes file, we can have many blocks, more than 100, and we have more than 100 executors starting and trying to fetch the data from the Hadoop file system, and each of executor for each block has 1/3 of probability of fetching data from the single server which we use it to create file. And it was not very obvious for us initially, and it caused a lot of troubles. Then we could not understand why it takes too long to load Bloom filter into memory. It's only 5 gigabytes, but it takes more than an hour just to load it. And after we analyzed the traffic, we understood that actually all the executors simultaneously were trying to load the data from a single server, and it was obviously overloaded. We actually mitigated it pretty easily just by increasing replication factor. Instead of creating default 3 replicas, we create 15 replicas for a Bloom filter, and the problem is still there, but the probability is not 1/3 but 1/15, and it's already manageable. And executors load Bloom filter in memory in 5 or so minutes, not more. But what we want to do is to create a fully distributed schema. It's suppose that we divide Bloom filter into ranges, because Bloom filter is actually a very big bit set, and we can divide this bit set into ranges and make multiple merges which are responsible each for a certain fragment of a Bloom filter. And in this case, the resulting file, the resulting Bloom filter will not contain a single file. It will contain multiple files for each segment. The merger will not be a bottleneck, and the loading process also won't overload the single server, even without increasing the replication factor. That's actually basically it. So just wrap up and key takeaways from the talk. So first thing, that graphs are actually very important and very useful source of information, and you can mine a lot and use this information to provide your users with better services. But graphs often tends to vastly explode when you try to analyze them. A lot of graph algorithms are n² or even n³ complexity in memory and in communication, and this makes the graph analysis really hard. But using some properties of the graph, you can actually speed it up, the analysis pipeline. For example, just by using symmetric property, we managed to reduce the execution time from 20 hours to 4 hours, which is already manageable. And using probabilistic data structures, we can do even better. And if we can tolerate some noise in the graph, we can even get the job done in 10 to 15 minutes. So that's it. Thank you for your attention. Any questions?
Is creation of Bloom filter included in these 15 minutes, or it's separate count?
No, it's not included, but it's not a long process, and we need to do it once, and we can reuse it. The Bloom filter construction takes about 20 minutes.
Okay. Then the question is, after graph created with Bloom filter, is it filtered additionally to make it not probabilistic but exact by verifying data?
Yes, we can get the exact answers if we're looking at this schema. Here we get an exact answer because we are using Bloom filter to filter irrelevant data before we are shuffling. And here in the shuffle we will include only relevant data, and as a result we have the precise subgraph. So here we get an exact answer. We can speed up by not doing shuffle at all, and in this case we will have an approximate answer.
Okay.
But here the answer is exact, so it does not include any additional edges.
Thank you for the presentation. Did you try some graph-oriented database such as dgraph or ArrayDB?
We made some experiments. It was long ago, but actually most databases, graph databases, they are not oriented on analytical workloads. For example, Neo4j is more oriented on a kind of business logic servicing. There are some packages dedicated to analytical workloads. For example, Apache Spark has a package graphics. There is a giraffe package and many more. We've tried them. We first tried them 5 years ago. At that time, it was not acceptable, so they're too immature. We've tried giraffe, I think, a year ago. It became better, but still we didn't manage to tune parameters properly to make it work fast. And we fall back to our custom Spark implementations, which are just tuned for our needs.
Thank you for the talk. Social network is continuously changing, and so the question is, how often do you recompute all these things, and have you tried to design any online solution?
Yes, of course. So since now it's an 1 hour job, it's recomputed daily. So each night we just recompute all the Ego subgraphs, and we actually export the results in a special storage, which is serving a business logic, and from there we can just query different information from Ego subgraph in order to improve our services. And in the runtime, we also had a very similar solution also about 5 or even more years ago in order to create the friends recommendation service. When we are creating a recommendation of a friends, we also need to traverse the graph, and in this case we're interested not only in internal edges but also in external edges. And but the real-time or runtime case and analytical time case, they're very different. In runtime case, in order to make it work, we typically use sampling and cutting. We do not always try to just expand all 5,000 of friends in order to find something else. We just sample a part, expand it, and try to mine something from the sample. And next time the query comes in, we can make a different sample. So in the runtime, we either use the pre-computed graph, Ego subgraphs, which are updated daily, or we just use sampling from the social graph itself.
Any more questions?
Sorry, might be I missed this information, but could you tell us the storage size for the initial graph and for Ego graph?
Yes, actually, after all the filters applied and with storage format I described, they're not that high. So the original social graph, it's about 200 gigabytes. The Ego subgraph is twice as large.
Thank you.
Can you tell the size of graph in edges and nodes?
Yes, we have, as far as I remember, more than 12 billions of links in a social subgraph and 100.5 million of nodes.
Okay, if you will have any questions and too shy to ask questions directly to Dmitry, one more.
I have a question related to the size of the database of the data graph. Maybe it's better to get, I don't know, 1 terabyte RAM and package graph efficiently and do all calculations without Spark.
Yes, it's possible. So actually we can put a machine with a terabyte of RAM and feed the graph there pretty easily. But this kind of process, it's harder to operationalize. So we actually do have a cluster and it's fault tolerant, and if a single worker fails, it doesn't mean anything. So all the things just keep going. If we have this huge machine, what if it fails? So we need to make one more machine close to it, and we need to create some process devoted to deciding which machine will do what in case of failure and etc. We actually do use these kind of machines for machine learning, and we have about 8 or 10, I don't remember, machines with half terabyte RAMs with GPU cards and huge cores, and with Python and data scientists use those machines to train some models, which is easier to experiment with on a single machine. But if we have a working algorithm in a distributed setting, we usually prefer it because it's more reliable and it's simpler to put it into operation.